So let's look at accelerating objects. And acceleration is just a vector quantity. Acceleration is really just defined as the change in velocity. Now this acceleration has a unit of meters per second squared, which is really just a meter per second per second. That's where we get the meters per second squared. Now we sometimes use other units as well, but that's the unit we're going to use for most of physics. And if we were putting that in an equation, acceleration uses the letter A. It is a vector, so it has an arrow over top, and it's defined as the change in velocity over the change in time, or the time interval. And there's the symbol that we're going to use for change in velocity over change in time. So let's look at this situation. A batter changes the velocity of a baseball by 55 meters per second during a 0.3 seconds. The bat is in contact with the ball. So our change in velocity is 55 meters per second, and our change in time is 0.03 seconds. So if we use the equation above, the acceleration is the change in velocity divided by the change in time, which is really just 55 meters per second divided by 0.03 seconds. And then all we have to do is take that, put it in your calculator, and you're going to get an acceleration of 18,333 meters per second squared. And changing the velocity of a baseball is going to put a huge acceleration on the object. Now, when we're looking at accelerating objects, we are going to be using the equation much like we had before. Acceleration is delta V over delta T. Now, change in velocity can also be defined as final velocity minus initial velocity over change in time. And this is the equation that we're going to use for most of our calculation. So you may have heard advertisements like this. A car maker advertises that its car can go from 0 to 100 kilometers in 3.2 seconds. This really is just a measure of the acceleration of that car, how fast it can get faster. Since acceleration is a vector quantity, when an object is in uniform motion, then we say both the magnitude and direction of the velocity are the same. So an object in uniform motion tells us that it's not moving. And what's not moving is both the magnitude and the direction of that object. In this case, the acceleration would be 0. Now, if either the magnitude, and the magnitude is really just the speed, or the direction change, then the object is accelerating. And you may have experienced this kind of acceleration anytime you go in a circle. An object moving at a constant speed in a circle is constantly accelerating because it's constantly changing its direction. Acceleration can actually be defined as either positive, negative, or 0, and that's how we're going to define acceleration. Positive acceleration. If an object is increasing velocity, and let's imagine the velocity was going in this direction, and we put some positive acceleration on it, it's going to be speeding up, increasing the velocity. If we have an object that's moving with uniform motion and there's no acceleration, no push on it, then the velocity will be constant. But if we have an acceleration that's negative, velocity going in this direction, acceleration going the other direction, then the object is slowing down. It is going opposite the direction of the movement. What we don't want to do is we don't want to use the word, though, deceleration. Deceleration is not a proper physics term. We want to use either positive, negative, or 0 acceleration. And let's use this to try an example. A car is initially traveling at a velocity of 52 kilometers an hour west. During a time interval of 15 seconds, it increases its velocity to 76 kilometers an hour west. What is the acceleration of the car? Well, what we always want to do to start is write down our given information. And we're told an initial velocity of this object of 52 kilometers an hour in the west direction. We're also told that the car has a final velocity. And the final velocity is 76 kilometers an hour, again in the west direction. We're given a time interval, a delta t, which is 15 seconds. And what we want to find is the acceleration of the object. And there's our given pieces of information. Again, you may want to utilize a strategy. 52 kilometers an hour. 76 kilometers an hour, and 15 seconds, and we're trying to find out what is the acceleration of the car. That is what we're trying to find out. Now, before we can move forward, though, we have to look at our units, because our velocity is in hours and our time is in seconds, and we don't really like that. So what we want to do is we actually want to take our velocity and convert it. And let's do a little bit of unit conversion here. 52 kilometers an hour. To do this unit conversion, all we have to do is take our kilometers and change them to meters, which is really just 1,000 meters. Take our hours, and remember an hour is 3,600 seconds. Change our hours to seconds. And in the end, what we're just going to calculate is 52 times 1,000 divided by 3,600, and we'll get our value of 14.4 meters per second. Well, we can now take that number and put our givens in terms of meters per second. 52 kilometers an hour, well, we just calculated that is 14.4 meters per second, still going in the west direction. If we do the exact same calculation, 76 times 1,000 divided by 3,600, we'll get 21.1 meters per second, again in the west direction. And now we can actually use this information and find an equation that will work for us to calculate the acceleration. So what we have to do is turn to our formula sheet and find a formula that'll help us determine that acceleration. Now, acceleration is velocity divided by time. Now, change in velocity, though, we don't have a value for change in velocity. But we can look over here and take our change in velocity value of V final minus V initial and actually replace it in this equation. We do a substitution. That allows us to write an equation for acceleration as V final minus V initial all divided by delta t. And those are all the given pieces of information we have. And we can just put our numbers in. 21.1 meters per second in the west direction minus 14.4 meters per second also in the west direction, all divided by our time of 15 seconds, which when we put that in our calculator and do the calculation following order of operations, we get a value of 0.44 meters per second squared. And that is the acceleration of this object. Now we're going to look at other questions and more details on this in class.